Hi guys, Ben Hurley here, and this is the first lesson on electronics. I just wanted to take you through everything on the lesson. All of these lessons have been written out on the website, hopefully so that they're understandable on their own, but I'm also going to make a little video just sort of reading through them, maybe expanding on a few points and working through the examples to hopefully make them a little bit easier to understand and digest. So let's have a look at the website. We're on hurleyrobotics.wordpress.com. I'm going to head over to electronics, the page there, and we'll look at the first lesson, Ohm's Law. Okay, now there's the old video, which I'll update with this one. Now seeing as it's the first lesson, I'm starting from square one. What is electricity? Now the main thing to understand about what is electricity is that electricity is the flow of electrons. Down here we've got an image of an atom. Atoms are the small particles that all matter is made up of. All stuff, everything that is stuff like metal, wood, plastic, concrete, air, water, even people, all of the stuff that things are made of is all made of these little itty bitty particles called, well, I shouldn't call them particles, they're called atoms. And the atoms themselves are made up of three different types of particles: protons, neutrons, and electrons. Now, protons have a positive charge, kind of like a north pole on a battery. Neutrons are a neutral charge, they don't have any charge. And the electrons spinning around the outside, they have a negative charge, kind of like the south pole on a battery, and just like on the south pole on a magnet. And just like magnets, the opposite poles attract and the same poles repel. So if we've got a positive and a negative, they'll attract each other, and two positives will repel, two negatives will also repel. Okay, now the number and the makeup of the protons, neutrons, and electrons determines what kind of material that the substance is. So I've given a couple of examples. Hydrogen consists of one proton, one electron, and no neutrons, whereas copper atoms consist of 29 protons, 34 neutrons, and 29 electrons. So that's how different types of material are made with different combinations of these particles. Right, now what we're interested in electronics is what things conduct electricity and what things don't conduct electricity. So things like copper, iron, aluminium, metals basically, their electrons, these spinny ones, they are more loosely attached. They are free to hop over and across from neighboring atoms to neighboring atoms. We just said that the flow of electrons is what electricity is. So materials that the electrons can hop across, they can conduct electricity, so they're called conductors. And other materials like plastic, wood, glass, their electrons are tightly bound to their nucleus and they don't want to hop around. They don't conduct electricity, so we call those ones insulators because they insulate against electric flow. Okay, now the best way to understand electricity is to think about it kind of like a pump and a water pipe system. Okay, we've got three characteristics. We've got the pushing force, that's like our pump pushing the water around the pipes. We've got the flow of the water, and here we've got a shrinkage of the pipe, which is resisting against the flow of the water. It's making it harder for the pump to push the water through. And in electronics, we call our pump our voltage. You might have heard of voltage as in a 9-volt battery, or other batteries might be 1.5 volts. Like most little batteries you put in a remote control or things like that are 1.5 volts. Little disc batteries that go in toys and watches and things, they're often 3 volts or 3.3 volts. Car batteries are usually 12 volts. Okay, now the water flowing through, that's our current. That's the electrons hopping across from atom to atom, flowing through our conductive wire, which is the pipe. And the shrinkage in the pipe, the resistance, is also a part of electricity. We often talk about the resistance to the flow of electricity, and that's quite important. That resistance to the electric flow helps us to add control to our circuit. So our three characteristics are voltage, our pushing force, the current, which is the flow of electricity, and the resistance to that flow. Okay, here's some example of simple circuits. We've got a battery, which is our voltage source, pushing the electricity along. We've got a switch which we can open to disconnect the wire so that the electricity can't flow all the way around. So when the positive and negative terminals of the battery are connected in a loop, that's called a circuit, and the electricity can flow from the positive end right round to the negative end because opposites attract. Okay, and we've got a light bulb which can turn on when the electricity is flowing and turn off when the switch cuts the circuit, and we've got our conductive wire as well. Here's another similar circuit. This is written in more proper electronic symbols. So we've got a symbol for a battery. This is actually two batteries with two long and short lines. That would be something like a remote control for a TV remote. You usually put two AA's or AAA's in them. We've got a switch. This is the symbol for a switch. You can see how it's currently breaking the circuit, and when that contact point touches there, it closes the loop, which closes the circuit and allows electricity to flow. This is an LED. We're all pretty familiar with LEDs. A lot of even household lights are being changed to LEDs these days. The little torch light on mobile phones is usually a very bright white LED. All sorts of lights use LEDs these days. And down here we've got the symbol for a resistor as well. We'll get into more about resistors in the next lesson after this. Okay, now Ohm's law, very important, discovered and published rather in 1827. Georg Ohm discovered the mathematical relationship between these three characteristics of electricity. So the mathematical relationship between volts, current, which is I, and resistance, which is R. Okay, now I've got this little diagram here which shows the formula in three different arrangements. So depending on which one you're wanting to find out, if you have the answers for the other two, you can figure out what the third one is. So the main one is volts equals current times resistance, V equals I times R. I usually remember this one because it kind of looks like VIP almost. If you pretend that R is a P, P just makes it sort of memorable. But in this triangle you can see how they've arranged it. We've got, if you're looking at V up top, then V equals I times R because they're at the same level next to each other, just like maths, two variables next to each other would be multiplied together. Okay, if we're looking at what I is, this is the current, then current is V divided by R, because in the triangle the V is on top over the R. So we've got I equals V divided by R, or V over R. And then also if we're wanting to find out what the resistance is down here, so R equals V divided by I. In the same way, V is on top, I is down bottom, so that's our fraction there. Okay. Now, what's the point of all this? How is this useful? Now, this is really useful for designing our circuits in all sorts of applications. The first one that we're going to be interested in is in designing a circuit to light up an LED, like in the one that we just saw. We can't just whack on any old resistor onto an LED circuit because LEDs are rated to only handle a certain amount of current, otherwise they will burn out and no longer be useful. So we want to protect our little LEDs when we're wiring them up. We don't want to waste them and destroy them and burn them out, otherwise we'll run out and we won't have any. So we need to know, so I've put in an example here. The ones that we have in our kits are 5mm LEDs, and they can handle a maximum of 20 milliamps of current. Okay, now when we're using this formula, we don't want to do our calculations in milliamps, which is thousandths of an amp. We want to do our calculations in amps. So 20 milliamps is going to be 0.02 amps, because once you get down to the point, the first column is going to be hundredths, next column is going to be first one is tenths, hundredths, and then thousandths. Okay, and we've got 20 milliamps, so that's in the tens column. Alrighty, so we want to keep the current at a maximum of 20 milliamps, otherwise we'll destroy our LED. Right, so if we wanted to create this circuit in real life, which we'll do in a couple lessons time, we want to select a battery and select a resistor so that we don't blow up our LED. Okay, now let's say for example I've got a 9-volt battery, okay, and we know that the current has to be no more than 20 milliamps or 0.02 amps. Okay, so we know the current, we know the voltage, we want to find out what resistor to select. So we need this form of the formula here. What is R for resistance? R equals V divided by I. So I'll get my calculator out. R equal V, which is 9, divided by our amps, which is 0.02, equals 450. So we need to make sure that our resistor in this circuit is at least 450 ohms is the measurement for resistance. We need to select a 450 ohm resistor or greater. So the greater the resistance, the less flow. Think about go back to that, putting a kink in a pipe. If you get a garden hose, if you kink it, you're making it smaller, you're adding resistance to the flow of the water, less water is going to come out. So less water or less electricity is safer for our poor little LED. So we want 450 or greater resistance for our resistor, whatever's closest that's handy we've got. Okay, so that's basically it. I've just written down here when we're writing about these three values, we use the abbreviations V for volts, so 9V stands for 9 volt, A for amps, so 0.02 capital A meaning amps, and then the omega symbol is the abbreviation symbol for ohms, so we need our 450 ohm resistor for this circuit. Okay, so I've made up a Google sheet, I think they're called, a Google sheet, Google form rather, with a few extra examples that you can have a go at. And here we are over here. You can pop your name and your school in here if you're from a school. I've given you the diagrams here with the three versions of the formula so you can see it pretty quick. And we've got 9 examples with different values so you can practice figuring out which one of these formulas we need to look up and then working out your answer. So how about I just go through one more? Go through the first one just as another example. So in this circuit here, it says up here I, which is current, equals 1 amp. How many volts is the battery? Okay, here's our circuit, there's our battery. It's not labeled, we need to figure that out. And over here the resistor is indicated, it is 10 ohms. So we know resistance, we know current, we need to find out the volts, and the V equals version is V equals I times R. So I is 1 times R, which is 10. 1 times 10 equals 10. So our volts for our battery must be a 10 volt battery in this circuit. Okay, so once you go through all of these examples and pop in your answer, you can click submit and it'll tell you how many of them you got right. Now I put in a few different versions of the answers. You can put in, so this answer is 10. You can type just 10, or you can type in 10V. Might be easiest just to do just the numbers for this one. So I can't remember whether I did capital V's and little v's are acceptable answers. Maybe just put in the numbers and that'll be recognized by the answers and mark them correctly. Alrighty, so that's it for our first lesson. I hope that was interesting, and I definitely know that will be very helpful later on when we start building real circuits. I'll just pop up in a friendlier view up there. Okay, that is probably the first step to really understand the nuts and bolts behind what's going on inside our electric circuits. We always want to keep in mind what's the voltage of our circuit, what components am I using, what should the current be, and making sure that we've got enough resistance in our current so as not to overload our components. Alrighty, thanks for watching guys. Enjoy that one, and I'll bring out the next lesson very soon. See ya.